Start? Or did that happen?
It's already working.
Oh, okay. Well, so yes, so the talk is called Khintchine types of translated hyperplanes, translated coordinate hyperplanes. And so I'll just vaguely say what the general problem is. So of course this is a Diophantine approximations talk. So the problem is to approximate points in RD, so d different numbers at the same time, by rational vectors. So by, say, P, a vector P over Q, with P, Q, integers. But I want to do this with one of the coordinates fixed. So with, say, x1, call it x fixed. So, I mean, of course, I'll be more precise as the talk progresses. But the point then is to, how to approximate many numbers at the same time if one of them has to be like the square root of 2 or something, or someone gives you the number. So let me just briefly give you the general setup here. I'll always denote by psi a function from the natural numbers into the positive real numbers, including 0. And say it's decreasing, or rather non-increasing. And this I will call an approximating function. So the thing we study is the following set, denoted with a W. So W sub D of psi, or W of psi, will be all the points in RD, such that this inequality Qx less than the value of this approximating function at Q is satisfied for infinitely many Q's. So, I mean, I guess this is a standard notation, but by Qx, I mean, you take, you multiply xq times and you look for the nearest integer lattice point and record the distance in the supernorm metric. Okay, I'll call these the psi approximable vectors. All right, what else do I want to say? Okay, well, anyway, so the whole talk is about that set. Right, and so the point is, I mean, you want to measure the size of it. So I guess what I take to be the background theorems for the rest of the talk would be first Khintchine's theorem. Of 1926, which tells us the measure of this set. So the statement is that if psi is an approximating function, then when we look at this set that I've just defined, and we want to know its measure, d-dimensional Lebesgue measure, then that's either it's either a full set or a null set. So null or full. And the thing that this depends on is the series corresponding to the approximating function that you started with. So you sum over all the natural numbers, and if that sum converges, then you know that the set of psi approximable vectors is null, and then in the other case it's full. So that's, all right, so I guess that's the first background theorem I wanted to say. So it's important that the function be a decreasing function, right? Okay, except in the null case. In the convergence case, it's just a consequence of Borel-Cantelli anyway, but it's necessary for the divergence case.
Not for
Except for, thanks. Except for in higher dimensions. So the other theorem I wanted to write up was Gallagher. So what I'll call Gallagher's theorem. So it's the same statement. So the theorem is that if D is at least 2, then we can dispense with the monotonicity assumption. So no need for monotonicity of psi in Khintchine's theorem. Okay. So as I said, those are the two background theorems. And so I can start stating more precisely what I mean by this problem of wanting to approximate numbers simultaneously. I guess I just want to maybe somehow say something like this Khintchine's theorem statement for this type of approximation. So let me define or talk about a notion called Khintchine types. So Khintchine type for divergence. So if we have a subset of Rn, or Rd, you can talk about whether or not it's Khintchine type for divergence. And let me just write what this means. So a manifold in Rd is of Khintchine type for divergence if almost every point on that manifold is psi approximable. Oh, sorry. Whenever this divergence condition from Khintchine's theorem is satisfied by that approximating function. Okay, so really the so the problem that I vaguely stated, I should say is really this, and the question is whether or not hyperplanes with one fixed coordinate are of Khintchine type for divergence. And of course the hope is, or I guess my hope is that they are. So let me give maybe some context. This has been studied especially for curved manifolds. So there's work of Beresnevich, Dickinson, and Delaney on this, I think 2006. And more recently, just Victor Beresnevich. In 2012. And if I just informally state the outcome of these papers, it's roughly saying that non-degenerate manifolds non-degenerate manifolds in Rd are of Khintchine type for divergence. Khintchine type for divergence. So the thing holds if the manifold is non-degenerate. Non-degenerate meaning, so this is a curvature condition. It means that a manifold is non-degenerate if it leaves every hyperplane. Move the upper board up. I'll move the lower board down. It doesn't go up any. I've been wondering why people weren't pushing it up higher, and that's why it doesn't go up. Okay, so, well, I guess that's context for what I want to say in the talk, right? Because now this problem, you know, like if you ask whether a hyperplane through RD through some fixed point is of Khintchine type for divergence, you're asking a question that's in the part that's not covered by these results, right? Because of course it's a hyperplane, so it doesn't leave every hyperplane.
What about the convergence?
What's it? That's for another talk, Anish. Yeah, and you could ask the same thing for Khintchine type for convergence, and of course people have studied this, you know, and the definition will be the same thing. If the convergence condition is satisfied from Khintchine's theorem, can you then assert that you know, a manifold is not psi approximable almost everywhere, just like Khintchine's theorem. That's been done for curves. It's Sanjay Villani and Bob Vaughn, I think. Okay, so I guess if I can erase the title. So of course now the problem is to consider whether or not these manifolds are of Khintchine type for divergence. Right, so if someone gives me an x, I would like to be able to say that indeed the hyperplane passing through that x is of Khintchine type for divergence. So that's the expectation. That they all are. But I guess I'm really only going to talk about evidence toward believing this. So maybe say you fail to prove the thing. So failing that, you can do other things. For example, what if you just manage to prove it for some x's? You know, for some special x's. Or, you know, you could so forget the definition Khintchine type for divergence, but just fix a function psi that satisfies a divergence condition and ask whether every hyperplane is psi approximable. So you could do it for some size. You know, this would be progress of a sort. I only bring it up because it's a situation I'm in. So let me state the results that I have in these categories. Oh, you know, I can push this one up. No, I'm done.
In the definition of Khintchine type divergence,
Yeah.
what's the dimension of a manifold?
Any dimension.
Any dimension?
Yeah.
But you still want the series to be the power of.
Yeah, to the power of d. You mean rather than the power of the manifold?
Yeah. Is it automatically true?
Yes, in the definition, you do want the power of d. for example, in the talk, I mean, this talk, it's the same situation. My manifolds are d minus one dimensional, yet I'm concerned with d powers diverging.
Yeah. So I
It's a
think,
stronger condition. The thing is, I mean, well, once the manifold's embedded, you're asking for much more than just.
right. I think the best way to see this is to consider what happens if you take a manifold and then translate it by a random point. So then almost every point of the translated manifold should behave like a generic point in space. And so therefore, this is the right condition to use.
Okay, let me state the first result. In fact, all of them. Okay, so the first one I guess will fit into this second category where we fix a psi. So let's let our approximating function be q log q to the power minus 1 over d, where d is at least 3. Somehow, by the way, this should be the first example you think of. If you just the function q to the power minus 1 over d is a bad example because Dirichlet's theorem already solves the problem directly. So somehow this should be the first example. And then in this case, we do get what we want. So I'll write it this way: that the d minus 1 dimensional Lebesgue measure of the set of psi approximable vectors intersected with a hyperplane of this type, of this form, is full for every x. Okay. So, all right, well, so the argument that I'm going to talk about today will prove this statement for every x that isn't a Liouville number. But it turns out that the Liouville case is taken care of automatically by Khintchine's transference principle. Just like TP does.
Also, the approximating rationals don't have to be on the manifold.
That's right.
I see. Okay.
Yeah. So Khintchine's theorem, Khintchine's transference principle takes care of x's of high Diophantine type. So, for example, the Liouville numbers, and I should thank David Simmons for pointing this out to me last week instead of waiting to do it now. So really, you should think of the talk as being, it's an argument for lower Diophantine types. In particular, for this theorem, I'll show you how to prove it for everything that isn't Liouville. Next, I guess maybe the next step up in generality of psi is to let psi be the following approximating function. So, okay, well, q log q, but then you could put in more logs, right? For example, you could put in log q. And you would still have the d power d's diverging in this series. So you could, do a bunch of these if you want, maybe s of them to the power minus 1 over d. Again, with d at least 3. And you can say the same thing. In other words, that almost every point on a translated coordinate hyperplane is psi approximable for x's whose, I'll define in a second, regular Diophantine type is greater than 1. Actually, I'm going to continue on this board and I'll just move it up. So by regular Diophantine type, I mean, similar to what is meant by usual Diophantine type. So regular diphentyne type. Maybe call it sigma tilde, in case later I call diphentyne type sigma. This will be the supremum of numbers tau, such that this inequality, okay, I guess now it's a real number, so forget the vector, is less than q to the minus tau. Not just infinitely often, but frequently. So on a set of positive lower asymptotic density in the continuance q sub k of x. Right, you write the continued fraction for x, you look at the convergence, and you know the convergence are giving you best approximations. And to say that a number has diphentyne type whatever tells you that you get an approximation infinitely often. So by regular diphentyne type, I just mean that it happens actually, so sort of frequently with respect to the continuance. And hopefully in the talk you'll see more or less why, or maybe I can convince you that these kinds of considerations come up naturally in the calculations. Lastly, I want to state one where psi is not restricted, but then on the other hand, the x's will be. So again, let d be at least 3. And psi an approximating function such that the divergence condition is satisfied. Okay. Then the same statement holds, so I'll just write same. In other words, the almost everywhere thing for the hyperplane for the following x's. And there's a list, of course. So the easiest is that, of course, if you chose a rational number to begin with, it's almost immediate. Second, any x of, I'll just write diphentyne type, less than the golden ratio, 1 plus root 5 over 2. Okay, this is kind of a funny one. The same statement, any x of diphentyne type less than 2, such that there exists some number r, such that, I'll write it this way, such that whenever a partial quotient of x exceeds r, we either have that the next two don't exceed r, or the next one is between 1 and r, but strictly it can't be 1. Which I know is, I guess, a funny condition, but maybe I should explicitly say where x has been written as a continuous fraction. Right, so these are just, I mean, you could think it's the x's whose continued fraction have some special boundary that you're jumping up and down, and you're skipping above and below as you write the continued fraction. Okay, and I'm going to squeeze one last one here, number 4. Any x, uncountably many x's of any diphentyne type. Okay, so though these methods, at least I can't see how they would prove it for every x of any diphentyne type, still, if you choose a diphentyne type, you can produce as many as you want. Yes?
So condition 2 gets you almost every x?
Yes. But so does Khintchine's theorem. Okay. Oh, and I want to remark too that this one, condition 2 is currently being pushed and I think promisingly, and this is in joint work with Fabian Swiss. Although I'm only going to talk about the proof, yes?
So maybe I'm missing something obvious, but I think 2 gets you more than Khintchine's theorem because you get it for all psi simultaneously because your condition's explicit. And in principle, even though for each psi, Khintchine's theorem gives you a full measure set of x, maybe for every x there's a bad psi.
Yeah, that's true. Well, this also represents more Hausdorff dimension than you would get automatically from Khintchine. So, okay. Anyway, so I guess I'm halfway through and almost halfway through my notes, so we're on track. Let me tell you how these things are proved.
Are there any bounds for the Hausdorff dimension of
Exceptional?
of the complements of your x?
Yeah, sure. Well, I mean, for example, so when I say that any x of dipentane type at least psi, well, there's a formula for the x's that don't hold that. It's from Yarnik. This is like the 1/2 plus whatever.
There's some outside.
Yeah. I mean, I typed it into a calculator once. I think here I'm missing 0.7 or something, some number like that. I don't know. The truth is that it should be true for every x, so I don't really want to know how much I'm missing just yet. Let me tell you the strategy. So this is how all of these, how I approach all of these. So we're given some psi, some approximating function with the divergence condition satisfied, and say we're also given some x, some number x. Right, so this will be the base point of our fiber, and let's define the following set: q sub x comma psi, or maybe I'll just write q sub x for brevity. This will be all the numbers q that approximate the number x to good enough for psi. So qx less than psi of q. So we consider this set, and then this will reappear again at the top. I'm sorry. So if it turns out that summing psi of q with the d minus first powers over this set q of x, so if it turns out that that sum diverges, then we can apply Gallagher's theorem, the one that I had written up about non-monotonic approximating functions. Well, you can just apply it to the fiber through x, right? And it would just yield the result immediately. I'll just write result. Okay? So the whole strategy, I mean, the problem boils down to showing that this is true, right? So show this. So given psi and given x, try to show that this is the case. And so maybe it makes sense that, well, we should see how big this set q of x is. Because if I just sum psi to the d minus 1 over all natural numbers, of course that would diverge because we've assumed already that the d powers diverge. So So I want to talk about how to describe this set Q of x. So this part of the talk is called the three gaps theorem. And sequences with bounded gap ratios. Okay. So here's how we'll deal with these things. So let x be given, the real number, that'll be the base point for our fiber. But now just, let's say it's irrational, because again, the rational case is anyway easy to dispose of without doing anything. So the three gaps theorem, if you don't know it, tells you that, so let's see if I label this point 0, that if I start with some number x, well, of course it corresponds to some point on the circle, x, and if I rotate by that x and consider iterates some number of times, maybe 3, maybe it's then 4, x, and then 5x, say. And then I went in and measured all the arc lengths that are produced by this partition, then you see at most 3 different arc lengths, right? So maybe if you measured that distance there, you would get some length L max, right? But it's the same distance as that one. So I'll call that L max of 5 because it's the longest arc length produced by a trajectory of length 5. There's some L min. So this would be L min of 5. And of course, there's usually there's one in between, like this one here maybe. I don't care too much about that one, just call it L, but forget about it immediately. So that's the three gaps theorem. It doesn't matter that it's 5 or 100. You would only ever get 3 different arc lengths. And it turns out that you could also say what the lengths of these arcs are, depending on the length of the trajectory. So let me define the following function. R sub x, the point of m, would be the ratio of the longest to the shortest arc length after looking at a trajectory of length m. Okay, and though I don't want to write down the formula, there is a pretty simple formula. For this. And maybe you can imagine that the formula involves the continued fraction expansion of the point x that you started out with. And so what I want to do is look at situations. Let me push this up. I want to look at situations where, in the picture that I drew on the circle, the arc lengths, the ratio of the longest to the shortest is bounded. Because then you can kind of, when you say that, you're really saying something about how dense these points are on the circle once you've drawn them. So let's pick some r, which is going to be our ratio bound, greater than 1. And this turns out to be the same r, by the way, that I just erased from that theorem statement where you have to bounce up and down above and below this r. So pick r, and let L sub n, and really these L sub n's maybe should have superscripts x and r, but I'll drop them, of course. So let L sub n be the trajectory lengths where qx from 1 to Ln has, I guess I could have been more concise, has r sub x Ln bounded by r. Okay, so Ln is the sequence where it's the times when the longest to the shortest arc is bounded by this pre-decided r that we pick, that we can pick. So if you wanted, you could pick it large or small. And in fact, it just so happens for the sake of my indexing that if I say r plus 2, it makes more sense. So pick some r greater than 1 and record the times when the ratio is bounded by r plus 2. And set sigma, let sigma sub n be the partial sums of those times. Right, so sigma would also have a superscript xr. Okay, and the point would be that the arc lengths for the trajectory from sigma sub n plus 1 to sigma sub n plus 1 in the subscript, they're comparable to L n plus 1 inverse. And there's an implied constant, which is essentially just r. Okay, and then of course the point of that is that when you have a picture on the circle and you want to know how many of the points land in an interval, then you can estimate it by knowing that they're all separated by something like this. I guess that's in spirit what's going on here. Let me define one last sequence before I state what I consider to be the key lemma in this strategy. So let's define A, which depends on x and r, to be a subset of the natural numbers. Well, okay, I wanted to make one quick note first. I'll finish this sentence in a second, but notice that Ln is a block sequence. Okay, because actually I did want to give a formula for the Ln's, right? So Ln is equal to a concatenation of blocks, etc. Again, I dropped superscripts xr. So by blocks, I mean blocks of consecutive natural numbers, right? Because if you're in a situation where the ratio is bounded by, say, 10, then probably many iterations will have the same property. The block B sub n plus 1 it starts at q sub k sub m plus 1 minus r q sub k sub m. I'll tell you what these things are, but I won't do that much with them, so don't worry about the subscripts. So it's this block of consecutive natural numbers, and I'll call that, for notation, L, right? It's one of the L's, so I'll call it L sub alpha m plus 1, L sub omega m plus 1. And let me tell you what these k sub m's are. Well, okay, the q sub k's are continuants of x when you write it out as a continued fraction. K sub m are the indices where, well, they're the indices just before a partial quotient exceeds r. So I'll say where a sub k sub m plus 1 is greater than r. Right, where, again, of course, x is the partial fraction. Okay. Well, I wanted to say it because I may say something later about it, but really the thing to remember is what the L's are, which is bounded ratio sequences. So let me go back now and define the set A of xr. So now let's define it. This is a subset of the natural numbers, which is also going to be a block sequence, A1, A2, dot, 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 and like everything else, and it depends on x and r. And A sub L will be the block sigma sub alpha L to sigma sub omega L, put -1, though that's not essential. So it's the consecutive block of natural numbers defined by these sigmas, right? So remember, the sigmas were just partial sums, right? So the bounded ratios give you a block sequence, and then you just generate a new block sequence by defining this thing, this set. Okay, so that's definitions. Let me tell you the key lemma for these results. It is that, well, if you remember the thing that we're interested in the first place, the sum over this set Q of x.
What's the alpha and omega?
Alpha and omega, they're sequences of integers, right? This sequence is L1, L2, L3, L4, L5, but it's block sequences, so a bunch of them are consecutive.
Right.
So just to call the beginning
Oh,
index
this is the
and end
definition.
index.
Oh, that's the definition.
Yeah, that's the definition, just to call it something. Yeah. Okay, so back to this. This is the sum that we're wanting to show diverges. These d minus first powers. We want to show this diverges so we can apply Gallagher and solve the problem. It turns out that this is or bounded below by the sum over q's in the sequence AXR of the d powers. Right, and then, of course, the implied constant would depend on R. Okay, so then the problem just becomes to apply this. So maybe you can write that. So the problem that I've been rewriting now becomes to show this thing diverges for some R.
Do you expect this sum diverges for every x or in every psi, or is this a limitation of the method?
I think it's a limitation of the method. It diverges for every x that I've been able to show it diverges for, but I think that it's, I don't know. It's definitely not, I mean, if it's only comparison from one side. Anyway, those results that I wrote up before, where you would restrict psi and then be able to show something for every x, or on the other hand, allow any approximating function psi, and then see what x's you could say something about. They all follow this game plan. We get to this key lemma, and we would like to show whether or not that sum on the right-hand side diverges. So I have time to tell you the ways to go. So I guess I'll talk about the most recent one, the most recent theorem first, which follows some density considerations. So if we're given the number x, which will be our base point, try to find some r greater than or equal to 1, such that the lower asymptotic density of this set AXR is positive. Okay, so that would be sufficient. And so I don't know if I have to write it, but I'll just quickly define it. So lower density is defined by lim_inf. Well, if it were just, if you don't know what, if it were just density, we would be wanting to measure the proportion of integers that we're taking up by our set. And kind of asymptotically, right? We would let n go to infinity, and that's the density, but this limit may not exist, so we take a limit and call it lower asymptotic density. And of course, there's also upper asymptotic density where we would take a lim sup. And it's well known that if you have a divergent series of a decreasing function, then any subseries along a set of positive lower asymptotic density also diverges, right? So that would be exactly what we're trying to show. Okay. So here's something about these sets A. This is a lemma. We have that for any x and any r, the set A that we've defined here, this block sequence has positive upper density. That's not too hard to show. But that, I mean, I guess that's maybe an annoying thing about block sequences, is that they can have any upper density and lower density, and they don't seem to do you any favors. So this is an example of that. All of these, it's easy to see have positive upper density, but it's not so easy to show that these A sets have positive lower density. But this lemma tells you something. I mean, maybe it's a modest thing, but if you take so maybe I'll write for any psi, an approximating function such that all convergent subseries are along the set of zero density. So Q in A, a subset of N. So if you have this property satisfied by your function, then we get the result on every fiber. So we'll just call it result on every fiber by this lemma and by this fact about positive lower asymptotic density, and then through Gallagher's theorem. But I'm not sure that's saying so much, right? I mean, if you think of examples of functions that have this, it's the first example you should think of is q to the power minus 1 over d. And as I said, Dirichlet's theorem already has solved this problem hundreds of years ago. But you could also put any positive number c here and make the same statement, and then maybe you would be saying something about badly approximable numbers and how they can't crowd hyperplanes. So it's something. Let me tell you the thing about Diophantine type. So as for lower asymptotic density, maybe here you'll get a flavor for how the rest of this game is played. So the other lemma says for lower asymptotic density, so for any x of Diophantine type less than the golden ratio, and any r, we do get the lower asymptotic density statement. The set AXR has positive lower asymptotic density, right? And then with the key lemma and then the Gallagher thing, then the problem is solved for these, which is that point in that theorem that I had written down. So I'll give you the idea of the proof and why Diophantine type considerations appear. I mean, it just follows from the fact that if you know the Diophantine type of a number, then this tells you how the continuance of that number grow. Growth rate of continuance. Okay, and so if we write down the set AXR, where we fixed some R at the beginning of this proof, and we know that this is a block sequence, So it goes by blocks like this, sigma alpha m, sigma omega m, minus 1, doesn't matter. Then the next block would be sigma alpha m plus 1 to sigma omega m plus 1 minus 1, etc. And you want to calculate the lower asymptotic density, then this is a lim-inf. And it's going to be realized by calculating on the left endpoints of these blocks. And so if you just look at what these things depend on, I wrote up a formula in terms of these q sub k sub m's. This one depends on continuance up to, so depends on continuance up to q sub k sub m. And this next one depends on continuance up to q sub k sub m plus 1. So the next one, right? So if you want this block sequence to have positive lower asymptotic density, well, the only thing that can go wrong is that the blocks get too far separated. Well, on the other hand, if you know the Diophantine type and therefore know that that these continuants don't grow too fast, then you can block that from happening. Right? So when you write down the calculations, you find that what you want is to be on this side of some polynomial, or on this side of the root of some polynomial, and so maybe I should just say that psi is the root of a polynomial. I mean, of course, I don't want to write the whole calculation down. The point is that you ask what Diophantine types would definitely guarantee that this separation wasn't too much to make the lower asymptotic density 0, and you find that if you're on this side of psi, phi, the golden ratio, then you're safe. So that's one way to go. Perhaps I should have looked at my notes. So there are a couple more things that you can do, which I hope will serve as explanation for the other results that I had written up. So the first thing was density considerations. The second thing is you can just proceed by a construction. So, so say we're given psi. We know from the key lemma what the sum is that we're trying to make blow up. So just start writing down partial quotients. I mean, choose them, and this is how our x will be chosen. This will end up being our x, such that the sum over this set A, x, r, at the beginning choose some r as well, so that this is forced to diverge. Okay, so somehow this is how you prove the statement I had about uncountably many numbers of any given Diophantine type. Because if I look back at what I've drawn here, so if you look at the partial sums, maybe the sum over the block A sub m. So that's a partial sum of what we're trying to sum. That would be the sum of this series just on this block, right? Well, we know that this last one depends on q sub k sub m. This first one depends on continuance only up to k sub q sub m minus 1 plus 1. And remember that these indices marked where the partial quotients exceed r. Right? So just start writing these partial quotients and say once, for example, when we're in the block, once we've entered this block, just write partial quotients that are less than or equal to r as long as you want, for 100 years maybe, until the sum over this block is large enough. And then write one that's greater than r to correspond to beginning the next block. I hope that's clear. I know I didn't write anything down. So I guess what I'm saying is that we we can make the length of the block arbitrarily long, just by waiting forever to get the next number that's greater than r. And furthermore, once we've made it arbitrarily long, we're free to choose the next number, the next partial quotient, right? And then we can then choose a sub k sub m plus 1 greater than r freely, right? So if you're trying to achieve some Diophantine type, then just choose your a sub k sub m plus 1 so that you achieve this growth rate of continuance, and then so that's your Diophantine type. And of course, you have uncountably many ways to run this procedure, because, you know, maybe if r is 3, then you could have chosen 1. Maybe it's clear that there are uncountably many, because we're choosing natural numbers at each step. And, well, I've got one short number 3 way to go, which is by direct calculation. Actually, I can just write it here. Right, as for the first results that I wrote down, where psi was explicit, it was q log q or something. Well, in these cases, you can just do direct calculation. Right, so I chose these psi's, but if someone gives you an actual function, then say, right, equals q log q, then just plug it in to the sum that we're trying to show that diverges. Right? You just plug it in. It's an explicit expression. So in these cases, the whole problem really becomes a calculation. You just show that the thing actually diverges, or, you know, maybe you might have to find the axis for which it diverges, but you find that actually they essentially all do. And so that proves the first two theorems. So, you know, that kind of procedure proves the first two theorems that I had mentioned. And since I have a minute, maybe I'll just close with some final remarks. So, okay, these final remarks are pretty informal, especially this one. But it's something that I like, which is so we can identify subsets of the naturals with points in the unit interval, because maybe I should say non-empty subsets or infinite subsets. Right, just like considering the dyadic expansions, every subset of the natural numbers is a point in the unit interval. And it turns out that there's a result by Salat that the set of convergent subseries of, say, so in the example that we're interested in, d, psi to the power d. So the set of convergent subseries of this corresponds to a subset of the interval of Hausdorff dimension 0. So, well, I like this because this a sub x of r, say we pick an r or something, this defines a map from our, you know, the numbers that are candidates for our base points to the interval. And, well, I don't know, I like the picture because really what we're trying to show is that this map here takes values outside of some set of Hausdorff dimension 0. But I mean, I don't know how easy that something like that is to show directly from looking at this map A. But but I think it's nice. Anyway, well, thank you.
Okay, any questions for Felipe?
So in the case when you only have the divergence on phi, you wrote down conditions 1, 2, like 1, 2, 3, 4. The first case was the rational case, x. So you have a
I think
rational
rational
hyperplane.
numbers, yeah.
And why is that true? And could the argument for that case be applied to say something that's super Liouville?
For the rationals, I just look at, I mean, you take, so if it's a rational x, then there's some common denominator, and if you just multiply by that, then okay, the sum that we want to diverge contains an arithmetic sequence along that common denominator. So this would diverge automatically. That's why.
Right?
That's why I said it was.
So you could probably use kind of something that's super Liouville. You could kind of
Yeah.
you just need these long sequences of.
Yeah. The thing about Liouville numbers, so Liouville numbers. That's true. They're very well approximable. I mean, I guess extremely is the right. I don't know, but along iterates that aren't close to rational, somehow there's a lot of them. They're few and far between. But then when they're there, maybe I guess they're frequent. I don't know. Maybe there's a way to do something with this.
I mean, because you're doing what you're doing for the bounded case or the divergent type cases. I think a similar kind of argument you could get it for the Liouville.
I'm sure you could. The other thing is that for, if psi is a reasonable function, for example, these q log q's, I made this remark that Khintchine's transference principle implies the result. In fact, so say you have a function like q log these, Khintchine's transference principle will tell you, will give the result for Diophantine type greater than the dimension. And in fact, it tells you more. It tells you that along those fibers, not only is almost every point psi approximable, but every point is. So the thing I'm trying to prove is even more than true for, say, Liouville numbers, if psi is a reasonable function. In general, maybe something like what you're suggesting. Yeah.
So you were always assuming that D is at least 3. Do you think it's also true for D? Should be true for D2?
I don't know. I go back and forth on it. Oh well.
But you just need that for Gallagher, right? Or,
I need it for Gallagher and another technical lemma, which I didn't mention. So it's not just Gallagher that's blocking me from doing the plane, but I guess it should be true on the plane. I'm hesitant to say so though, because non-monotonic Khintchine isn't true on the line. Things, I don't know. Intuition may fail you. I don't know. Although for reasonable functions like q log q, it's true on the plane for high enough Diophantine type by this Khintchine's transference principle. Or maybe.
Okay, any other questions? Okay, so let's thank Felipe.